Hi, I'm Atto, and I'm based in London right now.
Hi, I'm Paul, and I'm based in Burnley, Lancashire right now. So today we're going to have a look at redox half equations and how to balance them. We might have a look at oxidation states at the same time as well. So the first ones are fairly straightforward. We're just balancing the atoms and the charges. So if we have a look at the first one, sodium to Na plus, well, the sodium atoms or the sodiums are balanced. And now, so we just need to balance the charges in this, and we balance the charges by adding electrons. And I don't know, perhaps Atul, you could tell me where the electron would go.
So yeah, sodium being in group 1 has that one outer shell electron too many, I suppose. So it could lose one electron. So on the right hand side, you could put a plus E. Plus E minus for the charge here.
Yeah, and that would balance the charges because on the left-hand side with no charge, and on the right-hand side, the +1 and the -1 cancel each other out, so no charge on the right-hand side. Okay, so the next one, we've got PB4 plus to PB2 plus. So how about this time?
So just purely looking at from a charge point, if you could have, because you have the 4 plus on the left hand side, you could certainly put 2 electrons to bring it down to 2 plus on the right hand side. So on the left hand side, yeah, 2 electrons. Yeah.
So add 2 electrons here. And +4 take 2 is 2 plus on the left hand side, and we've got 2 plus on the right hand side. And next one, H2 to H plus.
Where you get the 2 hydrogen ions because of the molecular hydrogen becoming into 2 different ions, and in the process you get 2 electrons being released, so plus 2.
Excellent. So this time we had to balance the hydrogens. We hadn't had to do that previously with the sodium and lead.
Yeah.
And then the charges.
Yeah, so you get plus 2 electrons on the right hand side, so 2 electrons are released as a result here.
So because this is redox, this is oxidation and reduction. So has the hydrogen here been oxidized or reduced?
So the reduction is the gain of oxygen, the gain of electrons, and oxidation is the loss of electrons. So since electrons have been lost by the hydrogen atomic state or molecular state, so the hydrogen's being oxidized. Yeah.
Yeah, exactly. So we've had a loss of electrons, which is oxidation. We could also look at oxidation states here. So elements on their own have an oxidation state of 0, so they haven't been oxidized or reduced. And ions have an oxidation state of their charge, which is here is +1. And so from an oxidation state point of view, the hydrogen's gone from 0 to +1, so it's being oxidized. If it goes up, it's oxidized, goes down, reduced.
Right.
So next one, Br minus to Br2 bromine.
So again, it's to form molecular bromine, which has 2 atoms together, you must start off with 2 bromide ions on the left hand side.
Excellent.
And the bromide ions would have had an extra electron, which is why they are bromide ions each. So in order to form molecular bromine or atomic bromine in a molecule form, they would have lost 2 electrons in total, plus 2e on the right hand side again here.
Yeah. in terms of balancing charges, we've got -2 on the left-hand side and -2 on the right-hand side, so we can see that's correct. And what about oxidation and reduction here? Or oxidation or reduction, because these are half equations, so it will either be reduction or oxidation.
Yeah. So going with the oxidation state example, we've got on the left-hand side, you've got a state of -1, and on the right-hand side, you've got elemental bromine of 0. So again, a net change of +1. So by that definition, we'll go for oxidation again.
Yeah, excellent. And in the loss of, also we know that from the bromide ion has lost electrons, so oxidation is loss of electrons, so that also shows the oxidation as well. So this next one is trickier because we've got oxygen involved. So I'll demonstrate this one. So first of all, we've got 2 chromiums on the left, so we'll need 2 chromiums on the right. And then to balance the oxygens, we'll use water, because these are taking place in solution. So we can use water and we can use hydrogen ions to help us balance, as well as electrons. So the first thing we'll do, we've got 7 oxygens, so we'll add 7 waters to provide our 7 oxygens on the right-hand side. And that gives us 14 hydrogen atoms, 7 H2s. So we can add 14 hydrogen ions to the left-hand side. And now we just need to balance the charges. Our total charge on the left-hand side, we've got 14 plus 1, take 2, so that gives us 12 plus on the left-hand side. We've got 6 plus on the right-hand side, so if we add 6 electrons here, so we've added the 6 electrons, and now the charges on the left-hand side, 6 plus, the charges on the right-hand side, 6 plus. Now to see what's been oxidized and reduced, it's probably easier to see oxidation states here. So oxygen in a compound is always -2, well, nearly always -2. It's different in peroxide, but here it's -2. So all that would add up to -14. And so we know the chromium part must add up to 12 plus to give us the 2- overall charge. And there's 2 chromiums, so each of those will be +6. And the chromium on the right-hand side is easy. It's just the charge on the ion, which is +3. And so we can see that the chromium has gone down in oxidation state, so it must have been reduced. And we can also see that there's been a gain of electrons on the left-hand side, so that confirms the reduction.
Right.
Okay, so we'll just have a look at the last one now.
Yeah.
So we've got SO4 sulfate ions, SO4 2- going to sulfur. And Atul, seeing what we've just done there, and knowing you're a bit out of your comfort zone because you usually do GCSE chemistry, this is probably a little step up to A-level, just see if you could have a go at this half equation here.
Yeah. So going by the logic earlier, I got a sulfate ion going into sulfur there. I'm just using my pen. So presumably you get, yeah, we'll start the same way as before. So you had you add 7 waters because you had 7 oxygens there. So that means you can add 4 waters because of the 4 oxygens there. I'll write that out if that's 4 waters.
Excellent.
So because water is neutral, that means you must have had 8 H plus ions to start off with on the left hand side. With that same logic. So what did you have? You have 8 pluses, 2 minuses, and complete neutrals there. So you need more minuses basically. So you got 8 and minus 2 is yeah, so you need 6 more minuses to get a complete neutral. Yes, so again 6 electrons, I think. That's my, let me just double check that. 6, 2, yeah, that seems to work.
Yeah, that's excellent. And if we have a look at the sulfur here, on the left hand side, the sulfur on the right, the oxygen again will be minus 2, so that would give us an overall minus 8 for the oxygen, and so the sulfur, to give us an overall minus 2 charge on the ion, must be plus 6. And on the right hand side, it's just an element, and that's 0. So what does that tell us has happened to the sulfur?
So literally a reduction in the oxidation state, so going from a plus to a 0. So looks like a reduction to me, yeah.
That's exactly what it is, and we can see that there's been a gain of electrons on the left-hand side, so that would confirm the reduction as well.
Nice. Yeah, looks like a nice new novel method to work out these more complicated oxidation and reduction states here. Yeah. Great. Look forward to more of similar sort of videos for the next one. All right.
Yeah, next time we can look at combining these half equations and coming up with redox full equations.
Yeah. Source, I'm presuming applications like chemical reactions, but electrolysis as well, because that's where it comes up quite a lot, doesn't it? So,
yes, yeah. Yes, that's definitely an application of this.
Mm-hmm. Great, very useful to know. Look forward to the next bunch of videos on redox. Yeah.
Okay, thanks, Athel.
Cheers for now. Bye.